And now in this data transfer instructions, another instructions are LXI. See, LXI 16 LXI register pair comma 16-bit data here, not address, data. Okay, so here the 16-bit data, immediate data is stored into register pair. I will explain with one example. LXI B comma 1756H. Okay, 1756H. So this 1756H is it's not address location, it is immediate data. So this immediate data is we have to find out from this I symbol. I is mentioned, this is acts as immediate data. This immediate data is stored into one register pair. Which register pair? BC register pair. Then how to find out whether it is a register pair or only one register? Using this symbol, X symbol. Okay, whenever this X is mentioned, this we have to take always register pair. So now in this, okay, so BC register pair, 56H data is stored into BC register, C register, right? Similarly 17 is stored into B register. Okay, now it performs a IO read operation how many times? 2 times, right? So IO read operation is 2 times operation. That's why it requires 3 mission cycles. Number of byte instruction is 3 byte instruction. 1 byte is here, 1 byte is here, and totally 1 byte is here. 3 byte instruction and 3 mission cycles, and number of T states are 10 T states. Okay, load immediate with register pair. Load immediate data into register pair. This is the meaning of LXI. Okay, now another is there, LDAX. Load accumulator with register pair. Right? LDAX RP, space RP I am writing here. Load accumulator with register pair location. Okay, so register pair has some data that is acts as a address location. That address location data is stored into accumulator, right? So this is the operation. Register pair address location data is stored into accumulator, right? So this operation, now for this operation how many byte instruction? Number of bytes is only 1 byte because there is no data given here, right? And number of mission cycles, how many mission cycles? One fetching is compulsory, then it performs the memory reading, right? So register pair location, location means it takes the data from memory location, so 2 mission cycles. So 2 mission cycles, number of T states are 7 T states, right? LDAX. Okay, similarly exactly opposite to this one is STAX register pair. Okay, S indicates the store accumulator into register pair. Okay, now what I have to say here, accumulated data is stored into register pair location. Register pair location. Okay, see whenever I am writing like this 2 brackets, this is acts as a pointer, right? So accumulated data is stored into that place. Now it is 1 byte instruction. Number of mission cycles are 2 mission cycles, and number of T states are 70 states here. Okay, load operation, store operation. Load accumulator with register pair, store accumulator with register pair, exactly opposite operations now. Now another operation is XCHG, exchange. Exchange DE and HL register pairs. Okay, exchange DE and HL register pair. Then what happens here? Your DE register data is there, HL register data. This data is stored in this, and this data is stored in this here. Okay, completely interchanging the data of HL and DE register, just like it performs the swapping operation. To perform the swapping operation, so your data address locations data is not mentioned, so 1 byte instruction, and number of mission cycles, 1 mission cycles are enough because just copying the data, and number of T states are 4 T states. Then another important operation, push. Okay, push space register pair. Okay, this operation explains the pushes the register pair data, register pair data to stack pointer location. Okay, stack pointer location. See, remember here, stack pointer is always follows the LIFO method, last in first out, which follows the last in first out. Okay, which follows the last in first out method. That's why the starting address location of stack pointer is FFFFH. Okay, next it becomes decremented, next decremented, next decremented, like that. So it performs that type of operation. So here I am taking one example. In B register I am taking 50H. Okay, and C register is 79H. Two data I am taking here. B register is 50H and C register is 79H. Then this is memory location. These are memory. So in this memory already this data is stored. This is full now. Okay, this location is 2076H, right? Now this is 2075. Next location is 2074, and the next is 2073, and so on. So is there. Okay, now already the data is filled up here. That's why your stack pointer indicates this address location, 2075 location. It indicates this address location. Okay, now what is your stack pointer location? 2075H. Stack pointer is 16-bit register. That's why it stores 16-bit data. Now I'm performing operation, push operation, push B. Okay, push B. Then BC register pair here. It takes the BC register pair because B is nothing but here register pair. So in this higher order is stored into this location. So B register data is stored here. Then C register data is stored here. Okay, so what is B register data? 50H is stored here, right? Then C register data is 79H. Then what is the indication of the stack pointer? Here. Okay, now the stack pointer location is, what is the location? 2073H. 2073H. This operation explains Stack pointer is decremented by 2. Stack pointer is decremented by 2 because here one address location is this one, another address location is C register. So completely 2 bytes are stored here, and next available location is 2073. Then stack pointer is decremented by 2. Every push operation stack pointer is decremented by 2. Right? Now this is 1 byte instruction. Right? Why 1 byte? Because data is not mentioned. Then number of mission cycles, 3 mission cycles are required. 3 mission cycles, number of T states are 12 T states. Right? So here 12 T states. Why 12 T states? Because one is fetching operation. This is also bus fetching operation. Okay, bus fetching operation. Then memory write. Okay, memory write. 2 times memory write. Bus fetching is 6. Memory writing is 3 plus 3. Number of T states are here 12 T states. Push operation takes the 12 T states here. Okay. Now similarly we have another operation. That operation is a pop. Pop is exactly opposite to the push operation. Right. So every pop operation, register pair lower order is stored into stack pointer plus 1. Okay, means this register pair lower order into stack pointer. Then register pair higher order is stored into stack pointer plus 2. Is it okay? From register pair to stack pointer is push operation. Now stack pointer to register pair is pop operation. We got this point here. So now the symbol is we have to give this side here. Okay, not this side, because from the stack pointer location to register pair here, exactly opposite operation. From the memory location to here, this is our memory. This memory to C register, and this location to B register. Just I am assuming one example, B and C. Right? And here what happens? Your stack pointer is incremented by 2. Okay, every pop operation stack pointer is incremented by 2. Every push operation stack pointer is decremented by 2. Right? Now the number of bytes 1 byte instruction, number of mission cycles 3 mission cycles, but the number of T states are 10 T states only. Your bus of code fetch is not required. Right? Directly takes the from stack pointer location. But previously, first C register, B register, these two registers stack pointer location it has to store. Okay, so that's why pop operation takes the only 10T and push operation takes the 12 T states. Compared to pop operation, push operation takes more time. Okay, so all these are data transfer instruction sets. Now machine control instruction set. Here we have two operations. One is no operation and another is halt. Okay, NOP is nothing but no operation. So it does not perform the any other operation. That's why it's called a no operations. So but it takes some time. How much time? Say 1 mission cycle 4 T states. Okay, halt. This HLT explains the halt here. Halt, which stops the program. Stops the program here. Okay, this operation also same 1 and 4 T states. That live writing 1 byte instruction, 1 mission cycle and 4 T states. Okay, that mission cycle also only 1 byte. Okay, 1 mission cycle means fetching operation. Then similarly we have another instruction in space 8-bit address. Okay, here we have to give address. So here two instructions are there. one is in and another is out. These two instructions performs the operations with microprocessor with external devices. Microprocessor with external devices. So any data transferring in between microprocessor and external devices through accumulator is possible. Okay. So in explains the external device to the accumulator, means microprocessor accumulator. Out explains the accumulated data is stored into external device. That external device is other than the memory we are taking, like input device, output device, some display devices, all this here. Okay, the operation is here. 8-bit port, 8-bit port address. This address location data is stored into accumulator. Okay, your out operation is accumulated data is stored into 8-bit port address. Say I am writing here port address. Port address means some IO devices, external devices. Okay. Now all this here 8-bit address is there. Here also 8-bit address, right? So 8-bit address. So it requires 2-byte instructions. Okay. The number of mission cycles are 3 mission cycles. Why 3 mission cycles? First it has to read the address, 8-bit address. So IO read. Later the address location data is reading. So IO reading is there, IO reading. 2 times IO reading operation. So 1 is fetching cycle, 3 mission cycles it requires. Number of T states are 10 T states. Is it okay? So all these are also, we can call it as a mission control instruction set. Right? Another instruction set here, branch control instruction set. Branch control instruction set. This instruction set explains the assembler is jumping from one location to another location. Right? That's why again it is classified into 2 types. One is conditional, okay, unconditional. Conditional and unconditional instruction set. First we will go through the conditional. Conditional branch control instruction set. Conditional branch control instruction set, the standard syntax is J condition. Here we have to write condition. This is the standard syntax. J indicates the jump. Jump if condition is true. Okay, jump if condition is true. Okay, if the condition is true, then it performs the jumping operations. So condition is false, it does not perform the jumping operations. Right? One example, JC explains the jump if carry. Jump if carry explains the carry flag is 1. Okay, carry flag is 1, then the condition is true. Similarly, JNC, jump if no carry now. Jump if no carry. This explains the carry flag is 0. Carry flag is 0, then the condition is false. The condition is true. Okay, carry flag is 0, condition is true here. And here carry flag is 1, condition is true. JC and JNC. Right? Similarly, we have another instructions. JZ, J and Z. JZ means jump if 0 flag. Okay. J and Z is jump if not 0. What is the meaning of this one? 0 flag is 1 and here 0 flag is 0. See, all these conditional instructions are defined with all the flags except that auxiliary carry flag. Okay, except auxiliary carry flag, Remaining all the flags are defined here. Carry, no carry, 0, not 0, and parity, even parity, odd parity is there, right? Plus minus. Plus minus means sign flag. Okay, so all these are some conditional instruction set. And in this case, this conditional instruction set. So here the syntax is J condition, right? And if the condition is true, it has to jump which location? Some 16-bit address. Okay, it has to jump some 16-bit address. So it is 3-byte instruction, right? Because 16-bit address is there, so it is 3-byte instruction. And number of mission cycles are 3 mission cycles. Okay, number of t states are 10 t states. Okay, so this is for only true condition. If the condition is true, it takes like this. If the condition is false, it does not perform the jumping operation. So the number of byte is 3-byte instruction only, but it takes 1 mission cycle is less. 2 mission cycles. Number of t states, how many t states? 7 t states only. Okay, number of t states are 7 t states. This is condition is true and condition is false. Similarly, unconditional. Unconditional, 3 instructions we are using. One is jump space 16-bit address. Okay, without checking condition, directly it performs the jumping operation to this 16-bit address. This is the function of jump here. Okay, condition is not required. So this is completely 3-byte instruction, 3 mission cycles, right? Number of t states are 10 t states. Okay, another important unconditional is call. 16-bit address, right? So call 16-bit address, this is 3-byte instruction. Number of mission cycles are 5 mission cycles, but number of t states are 18 t states. Okay, one of the largest time taking instruction. Okay, largest time taking instruction is call instruction only. So the operation is like this. Suppose here I am using call, then it jumps to the main route into the subroutine. This is your subroutine, and after completing a subroutine, again it come back to this position using return instruction. Okay, again it continues here, this operation. So here we can write return also one instruction set. Return is address location is not required here, directly 1-byte instruction, and 3 mission cycles, and number of t states are 10 t states, right? So all these are branch control instructions. Then another instruction is there, the DAA, decimal adjust accumulator after addition. Okay, after addition operation, accumulated data is converted into decimal data. This is the general function of the instruction. Okay, and this instruction, decimal adjuster after addition, this takes the 1 byte and 1 mission cycle, and number of t states are 4 t states. Okay, this is used after addition operation only. After addition operation, this is used here. Okay, so after addition operation, the result is in terms of hexadecimal format. this hexadecimal data is converted into a decimal data. One example I am taking here. See, after addition operation, I am assuming the result is stored into accumulator, right? So accumulated data is, now I am taking 5AH, right? Then I am using draw instruction. This draw instruction compares every nibble means 4 bits, every nibble to the 9. Okay, so now initially it compares the A data. A is greater than the 9, so A is greater than the 9, that's why this A data is adds with 6. Now it becomes 10, right? Again this one is stored added with this one, 5A. Now here 6 is added. Now this is 0 and here 1. 1 plus 1 is 6. Okay. Now what is the result now? 60H. Right? So after this addition operation, result hexadecimal is there. Hexadecimal data is converted into decimal representation. Now listen here. I am taking one example program. This example program is, okay, MVI A, 18H, MVI B, 36H, add B, DAA, this instruction. See, complete operation I am writing here. So, first instruction, MVI A, 18H, accumulator, 18 data is stored into accumulator. So, accumulator capacity is now 18, right? Similarly, MVI B, 36H, then B register data is now 36H. Then add B, both are added. Initially I am taking accumulated data 0, 0, 0, 1, 8 is 1, 0, 0, 0. Similarly, B register data 3, 0, 0, 1, 1, 6 is 0, 1, 1, 0. Both are added. The result is 0, 1, 1, 1 and 0 carry 1, 0 carry 1, 1, 0. This is stored into accumulator. Now what is the capacity of the accumulator? 4EH. See, after this operation, accumulator is 4EH. Now the instruction is used here, DAA. So DAA used is, then it converts the accumulated data into, means hexadecimal data into decimal. First it compares the E with 9, right? This E is greater than the 9, right? So E is greater than the 9, that's why this is added with 6. E plus 6. Okay, so E is 14 and 14 plus 6 is 20. 20 is converted into hexadecimal. Now it becomes the 1/4. See, what is the equivalent data E in terms of decimal? 14. That 14 indirectly it mentions here. Right? Now 4 plus 1 is 5, 4H. Then the question is given here. The previous gate question. After this program, the status of accumulator is given like this. So it is representation is in terms of hexadecimal representation, but the data is in terms of decimal. Means your data is used, numbers are only 0 to 9 are used. Only 0 to 9. So then what is the result now? Accumulator is 5, 4H. Okay. So in that result, you have to write here 5, 4H. This is previous gate question. Okay, previous gate question. Now we will discuss some previous gate questions using all the instruction set, because up to now we studied all the instruction set: arithmetical instructions, data transfer, logical instructions, mission control instructions, and branch control instructions. Using these instructions, how to write program, then which type of questions are expected for gate point of view, right? That part we will discuss some programs with previous gate examples. Okay.